we have just a little bit to go in chapter 6 in terms of uh, molecular polarity, which I think is where we kind of left off. So just to finish up that chapter, then we will be going to chapter 8, which is gases. A reminder, as I mentioned, I think last week and so forth, there is chapter 7 was pre-recorded because of the exam and everything else. Just again, try to keep us on pace. So there's just 2 lectures from chapter 7 that were pre-recorded. So make sure again that you do watch them. You're responsible for them. And I think perhaps maybe during discussion this week, maybe we'll go over some of those highlights of some of the stuff that's in those lectures. But again, from here, we will be going to chapter 8. All right, so last time we finished up talking about really drawing Lewis structures. We talked about sort of geometry associated with those Lewis structures. And really the last thing in terms of bonding that we need to sort of cover from that chapter is what is known as polarity or molecular polarity. And when we talk about molecular polarity, and again, this is really the last part there, chapter 6, molecular polarity. What we're talking about is really looking at the entire molecule as a whole and trying to decide if, as a whole, overall, with all the bonds that are there in that particular molecule, is the molecule going to be polar, which means that there will be unequal sharing of electrons as a whole in the molecule. Part of the molecule will be more negative, part will be more positive. Or is the molecule as a whole nonpolar, which means, again, it's essentially neutral, equal sharing of electrons. And it sort of relates to the bond polarity. If you remember, we did sort of those differences in electronegativity values. And again, we use those arrows, those bond dipole arrows. Again, it points to the more negative side, and the side that's more positive, it points that way. Remember, if it's like above 0.4, it's a polar bond. If it's below 0.4, it's a nonpolar bond. Now, the easiest ones in terms of molecular polarity to decide if something is polar or nonpolar are diatomic molecules. And diatomic molecules obviously only have 2 things attached. So if we look at something like we've seen before, H2 or F2, a little sketching here. And when we look at these molecules, a couple really important things. First off, we would, in this case, want to look and see if it has polar bonds. So if we look at the bond here between the hydrogen, or even between the 2 fluorines, we should know, based on sort of the difference in electronegativity, you'll get a difference of 0 in this particular case, which means in each of these cases, these are nonpolar bonds. Now, the nice thing sort of about a diatomic molecule is when we look at the entire molecule as a whole, that is the one and only bond in that molecule, which means it makes it really simple when we look at a diatomic molecule to try to figure out, is it polar or nonpolar? And it's simple because it only really has one bond, which means if this bond is nonpolar, and that's the only bond in the entire molecule, either one of these guys, that means that in each of these cases, this would be a nonpolar molecule, which means we would expect as a whole in each of these cases that the electrons are distributed pretty much equally over the entire sort of structure. Now, as we talked about when we're talking about sort of bond polarity, if we swap out a hydrogen for a fluorine, for example, there is definitely, when we look at this bond, this is a polar bond. And if you remember the difference in electronegativity, if we calculated it, it was something like 1.9, which is a polar bond. We could draw that arrow pointing towards the more negative side here, which is fluorine. And really, for the same reasoning here, because this is a diatomic molecule and because pretty much that one polar bond is the only bond we see in the entire molecule, we can make another pretty simple guess here that this molecule here is going to be a polar molecule. And really the reason is because the one and only bond in it is polar. And what it means in this case is really the bond polarity and the molecular polarity are the same here. The fluorine side of this molecule is more negative because the electrons are going that way. The hydrogen side is more positive. So diatomic molecules are really the easiest of any of them to determine whether or not the molecule as a whole is polar or non-polar. And again, because it has only one bond, if you're able to identify that one bond as being polar, then the molecule will be polar. If you're able to identify that one and only bond in it as being non-polar, then the molecule itself would be non-polar. Any questions on diatomic molecules and polarity? By the way, if a molecule is polar, it has what is referred to as a dipole moment. So a dipole moment is represented by this arrow, and sometimes represent it. In a non-polar molecule, because there's equal sharing, there is no dipole moment. There's no side that's more negative or positive, so we don't see that. Now, if everybody was that pretty straightforward, that would be great, but of course it is not. So when we get 3 or more atoms in a molecule, you really have to look at 2 things where you're trying to decide about molecular polarity. The first thing is, does it have polar bonds? So clearly, if the answer there is no, then you can pretty much stop. It's going to be a non-polar molecule. If the answer is yes, then you really need to go to number 2 here. And number 2 is you have to look at the molecular geometry. So if something has a polar bond, it may be polar, it may be non-polar, but you do have to definitely look at the molecular geometry to help you decide that. And the way we do that is pretty straightforward here. Let's take a look at one. Let's take a look at CO2, which is a pretty good example. We draw the Lewis structure for CO2. It looks something like this. And in terms of bond polarity, if we use that table, you don't really even need to use the table here. If you look at the periodic table, you will see carbon, nitrogen, and oxygen. So when we're trying to decide, is it a polar bond between these two, because they are in the same period, we know it's going to be a polar bond, and oxygen is further to the right, which means it's going to be more electronegative. So we would be able to draw those bond dipole arrows heading towards the oxygen, which is more electronegative. So in terms of CO2, yes is the answer to polar bonds. So again, you may be thinking it has polar bonds, so it would definitely make sense that it is a polar molecule. And in a case like this, we do need to go to kind of the second thing here and look at the molecular geometry. And in this case, if we look at the center atom, it has 2 electron pairs. Remember, double bonds and triple bonds count as 1, and 2 bonds. So the molecular geometry of this guy is actually linear, which is a straight line. So essentially what we got going on here is we got like a straight line, and we got oxygen on one side kind of pulling. We have oxygen on the other side pulling, and I am really pulling on my pen here. And you can see my pen is really not going anywhere. And this is a very good example that you can have a molecule just like this guy here, CO2, that has polar bonds, but the actual polarity of the overall molecule is non-polar. So this would actually be a non-polar bond. I'm sorry, non-polar molecule. And that is because although there are polar bonds, they're basically going equal and opposite of each other, and they're canceling each other out. So sometimes people think about like pulling on a rope. So if you think of like 2 people pulling on a rope in a tug of war, and there's like a little flag in the middle, and if both people pull the rope in opposite directions equally, the flag's basically going to sit there. It's not going to go one way or the other. And because they're basically canceling out each other out. And that's the same thing that's happened here. Although it does have polar bonds, they're essentially, because of the geometry, canceling one another out. And that happens whenever we have these guys here, which are really vectors. And these are vectors, which from physics means that they have direction, they have magnitude. And again, in certain cases, they can add to each other and make it bigger. And in other cases, they can cancel each other out. In cases where they cancel each other out is always when they're sort of oppositely pulling in equal and opposite directions, or even if they're pushing in equal and opposite directions. So if you think about like a swinging door that just swings, if you have two people on opposite sides of the door pushing equally, the door is just going to kind of sit there, right? It's not going to open, it's not going to shut, because they're canceling each other out. So CO2, a very good example that although it has polar bonds, it does not necessarily mean that the actual molecule itself will be polar. If we look at something like water, for example, water here has polar bonds. Again, the bond between oxygen and hydrogen are polar. Oxygen further to the right than hydrogen on the periodic table. So if we were to draw those arrows, they would be heading towards the oxygen here. And basically, in this case, it does have polar bonds. So just like the other one, yes, we do have polar bonds. We need to look at the geometry here. That is 4 electron pairs. That is 2 bonds. That is bent or V-shaped is the geometry. So in this situation, we have more of a bent or V-shaped type of situation. We got kind of everybody heading towards the top. You can almost imagine if you had this like V and everybody was kind of going to the top, and you just pulled directly from the top, the whole thing would sort of move. And what ends up happening here is water actually does that. These two dipoles, because they're not equal and opposite of each other, they actually do add to one another, and they create what is known as a dipole moment, very badly drawn there, going through water, where the oxygen side of water is more negative and the hydrogen side of water is more positive. In case you're curious how that works, you take the guy right here and you draw it. You take the guy over here and you put it to the end of it and draw it in its direction. And then they end up adding to one another, heading in this direction, which is the overall dipole moment. Again, in that case here, they're going opposites of each other. They basically subtract each other out. So in this case, because of the geometry and because it has polar bonds, water is a polar molecule, where again, there's unequal sharing of the electrons as a whole over the entire thing. And the oxygen is more negative, because basically what we're saying is in the entire molecule, we have a greater amount of electrons hanging out this way than we do down here. And again, that's going to create an area in water that is more negative. And again, obviously the hydrogen being more positive. Any questions on that there? Now, most people, myself included, really don't like to draw vectors and do those things. So there should be an easier way perhaps to do it. And there is, that works pretty much most of the time. There are certain geometries which are referred to as being symmetrical geometries. And what we're talking about here are the molecular geometries. And a couple of those symmetrical geometries are trigonal planar and tetrahedral. And really what both of these guys sort of have in common, if you remember sort of what they look like, is when you draw the Lewis structure, there are no non-bonding electrons on the center atom.
Like, you know, segregated.
And if you have that sort of, please keep yourselves muted. Yes, thank you. If you if you have this situation where there's no non-bonding electrons on the center atom and everything on the outside is the same atom, this will basically lead to a very symmetrical situation where everybody is equal and opposite of each other, and it will basically be a nonpolar molecule. So for example, if we draw this guy here and we look at this guy, between carbon and fluorine, fluorine is more electronegative. And we would have definitely polar bonds in this case. And they would be heading towards the fluorines. But when we look at the center atom, this is basically going to be tetrahedral geometry. All those fluorines are essentially going to be equal and opposite of each other. So like the two will pull equal and opposite. The other two will also pull equal and opposite. So I do not see any dots here. Everybody on the outside is the same. They will cancel each other out, and this will be a non-polar molecule. Now, what happens if I take one of those fluorines and replace it with a hydrogen? In this particular case, we will still have those 3 polar bonds. A reminder that the bond between carbon and hydrogen is non-polar, 0.4 difference. So in this particular case, by removing one of those fluorines and replacing it with hydrogen, those 3 fluorines on sort of this side, if you will, those guys are all pulling sort of in that direction. And we really have nobody kind of pulling back the other way. So again, if you kind of go back to the tug of war example, you kind of have like 3 people on one side, 1 person on the other side. The 3 people are going to be able to pull probably that 1 person, across into the mud. And that's sort of what happens here. So we go from a nonpolar molecule to a polar molecule in this case. So if you have one of these geometries and you do not see dots on the center atom, when you draw your Lewis structure, everything on the outside is the same element. It's a pretty safe bet to say that it's going to be a nonpolar molecule. If you have no dots on your central atom, when you draw your Lewis structure and everybody on the outside are not the same element, then it's a pretty safe bet that it's going to be a polar molecule. Any questions on that there? So because we have some symmetrical geometries, we also have some unsymmetrical geometries. And I think what I'll do is kind of put it into here. So some unsymmetrical geometries. And again, we're looking at molecular geometries. That's your trigonal pyramid. That is your angular. That is your bent or V-shaped. And I think that's all we did in this class. And basically what all these have in common is when you draw your Lewis structure, there are non-bonding electrons on the center atom. And if everybody is the same on the outside, it will be polar, the molecule. So for example, if we go back to here, we look at water, which is what we had here. We look at the center atom, which is, I'll redraw it over here. Center atom has dots. We have the same element on each side. It is going to be a polar molecule. So really what that leaves you in terms of molecular polarity is linear, which is a straight line, which is pretty easy. A straight line is if they go in opposite of each other, like in CO2, they will cancel each other out. If they're going towards each other, they will also cancel each other out and be nonpolar. It is possible in a linear situation that everybody is heading in the same direction. And if that is the case, then it would be a polar molecule. So that is sort of the straightforward way to do it. And pretty much you'll be okay in every of those situations. If you draw your Lewis structure, no dots, everybody on the outside is the same, going to be a nonpolar molecule. Lewis structure, no dots, everybody on the outside is different, or at least one thing is different, going to be a polar molecule. And if you draw your Lewis structure and you do have dots on the center atom and everybody on the outside is the same, going to be a polar molecule in that case. So if we look at some of the ones we drew, I think earlier on in this chapter, you know, if we look at something like this, look at something like this, look at something like this. We'll look at something like we'll do this. Maybe we'll add let's see that. I'll want this one too. And I think we drew this too. All right, so take a second here and decide based on what we're looking at there. Are these a polar molecule, non-polar molecule? So take a moment or two and see what you come up with. I see all of the elements on the outside are the same. That means that's an unsymmetrical geometry. That is going to be a polar molecule. I look at the center atom of the next one. I see dots. I see everybody on the outside is the same. That also is going to be an unsymmetrical geometry, and that is going to lead us to a polar molecule. I look at the central atom of this one. I do not see dots, and I see that everybody on the outside is the same element. That means that this is going to be a symmetrical geometry. And based on geometry here, this would be a non-polar molecule. Any question on those three there? This is a diatomic molecule, which means I simply need to decide, is this bond polar or non-polar? And since it is two nitrogens, I know that that bond should be a non-polar bond. And because that's the only bond in this entire molecule, this guy should also be a non-polar molecule. Coming up here to the top, we got our central atom. I see dots. I see the same element on the outside. That tells me it's unsymmetrical, and this is going to be a polar molecule. And lastly here, I see no dots. Everybody on the outside is the same. That is going to be a non-polar molecule. In addition, this molecule here has no polar bonds to begin with, as the carbon-hydrogen bond on all of those are non-polar, which means it definitely should be a non-polar. That's probably the best way to do molecular polarity. Draw a good Lewis structure, look for dots or no dots, and what's attached on the outside. Question on molecular polarity there. Okay, so as I mentioned, this is sort of some of the stuff we talked about. We do classify the molecules as polar, which again means there is a side that's more negative and a side that's more positive. And in the case here of SO2, it would be angular, and it is the oxygens here that are more negative. Sulfur is more positive in that case. Nonpolar molecules have nonpolar bonds and no bond dipoles. They all cancel out. Polar molecules do have that dipole moment where they really don't cancel out. And again, here's a few more examples. If we look at this, we see no dots on the central atom, but we see that all of the outside atoms are not the same. And that means that this molecule here would be a polar molecule as we see. We see absolutely no dots. Everybody on the outside is exactly the same. They will all cancel each other out. That is our symmetrical trigonal planar geometry, our triangle. So basically everybody here is a triangle at the corners of a triangle, and they all pull equally and cancel out. This is the one we did before. I see dots. I see the same on the outside, going to be a polar molecule. Here I see no dots, but not everything on the outside is the same. And again, that now would make it a polar molecule. Again, these guys would be kind of pulling this way. These hydrogens are not doing very much to pull the opposite way. So again, if you sort of think about it like pulling a string, everybody pulls sort of in one direction, nobody really pulling back. The whole thing is going to kind of move, and it would be polar. Any questions on how to figure out molecular polarity, which is the entire molecule? Are we sharing the electrons equally or unequally? Any questions on that? Okay. And that does officially wrap up chapter 6. And as I mentioned earlier at the start, again, chapter 7, there's 2 lectures that were recorded. So again, since we had the exam last week, we didn't really have lecture. So to keep us on pace, we're going to go to chapter 8, but do make sure that you watch those lectures. You are responsible for the material in there. And then, like I said, perhaps this week here, we'll try to go over some of that stuff that's in those chapters in a sort of informal way, just to make sure, again, we're kind of on the same page. Any questions on any of that stuff? Okay, so this is chapter 8, which is gases. So obviously, we're going to be talking about gases that are obviously in the gas state. So remember that when we do get to the gas state, that's probably not a good drawing. When we get to the gas state, everybody has basically broken apart from one another. They are flying around as opposed to, say, in the liquid state, where everybody's still relatively close to one another. And obviously, we transition into the gas state as we go through the process of evaporation or vaporization, which happens at the normal boiling point of a substance. As those molecules are flying around, there's going to be collisions with the container, perhaps collisions with themselves. And it's those collisions that we associate with the pressure of gases. So let us talk about really what substances sort of exist as gases under normal conditions. So under normal conditions, which is sort of everyday room temperature sort of conditions, and that's a little bit different than what we'll talk about later on this chapter, but that usually refers to, again, your basic normal day conditions, kind of conditions that typically, if you look up table values in a chemistry book, that is 1 atmosphere, which is a unit of pressure. So ATM is an atmosphere. And 25 degrees Celsius. And under normal conditions like that, at 25 degrees Celsius and 1 atmosphere, we typically do not find ionic compounds going into the gas phase. And that is because they are held together, as we talked about, by very, very strong positive and negative attraction, those electrostatic forces. That is a really, really strong attraction. And to basically get those guys to kind of go away from each other, it would take a lot of energy to do that. And under normal conditions, like 25 degrees Celsius and 1 atmosphere, in terms of the pressure, we typically don't see that. It will actually start to melt because they're still associated with each other, then go into the gas phase. We know that, for example, if you just think about salt, basically, right? Sodium chloride. We put that on something hot or heat it up or fry it, whatever we want to do, right? We really don't get sodium chloride to go into the gas phase or anything like that. It's still there on it. It would not be good probably if it did that. It basically will hang out there. We also know, perhaps, if you've ever taken salt water, which is basically sodium ions surrounded by water, and water, as we just talked about, is polar. So the oxygen side of water basically surrounds the positive ion, and the positive side of water surrounds the negative ion. And here, this is really the process of dissolving. And if you ever heated this up, what happens is we start evaporating off all the waters that are surrounding them. And really, these two guys will come back together because there's a really strong attraction. And if you continue to heat this, this will never go into really the gas phase or anything like that. It will start to sort of melt. So it's a common experiment sometimes that they do salt water and then kind of evaporate it off. And you're left with really this salty residue that's left over at that point. Now, when we talk about molecular compounds, which are guys that are basically sharing electrons, those guys are very different in terms of their properties. There are certain molecular compounds which right off the bat are in gases. So things like carbon monoxide, carbon dioxide, hydrogen chloride gas, ammonia, which is NH3, methane, which is the simplest organic sort of molecule you could have. These are all gases. But a major difference is at room temperature, a majority of molecular compounds are liquids and solids. The major difference, though, is the way that a molecular compound is held together to another molecular compound. For example, like water. The way these two guys are attracted to each other, positive side of one water is attracted to the negative side of another, and that is what really holds these sort of waters together. Now, this type of bond here is, as we'll talk about in a later chapter, this is what is known as a intermolecular force. And that is the force that basically holds two molecules together. And that force is much weaker than an intramolecular force, which are like these guys here. These are intramolecular force, which means within the molecule. So what happens when we heat water? Well, when we heat water, because of the weaker bond between one water molecule and another, we actually break this bond first. And what ends up happening is that then liberates this water and this water from one another, and they could go off now into the gas phase. And that's obviously very easy to do. You do it all the time when you boil water. So it doesn't take a tremendous amount of energy to take something that is molecular like water and convert it into the gas phase. And that is much easily done with molecular compounds and ionic compounds. And that is because the force that holds the sodium ion and the chloride ion together way stronger than the force that holds these two waters together. And again, that's why it's much easier to convert a molecular compound into a gas than trying to convert an ionic compound into a gas. Now, substances that are found in gases under normal conditions. We have our diatomic molecules that we've talked about a number of times throughout the semester here. And again, remember, these are pretty much how these guys are found uncombined by themselves. Hydrogen gas, nitrogen gas, oxygen gas, fluorine gas, and chlorine gas. O3 is ozone, like the ozone layer, and that is a gas as well. And then obviously group 8 on our periodic table are noble gases, are helium, neon, argon, krypton, xenon, and radon. And again, that does remind me, some of you did email me about the exam and that question. I definitely, when I get a chance, we'll go look at it and correct it. Looks like the computer marked it wrong, incorrectly. Again, the noble gases are group 8. I think it was number 6 on the multiple choice. So I haven't had a chance to do that yet, but I definitely will go back and adjust everybody's score accordingly. On the periodic table, here's where we see our elements that are gases under normal conditions. And again, we see our hydrogen. And again, all these guys are really diatomic. These guys are what are referred to as being monoatomic gases. They basically just come as ones. And again, those noble gases are pretty much, as we talked about in bonding, what everybody is trying to achieve. And also, again, they really don't combine very much with anybody else. This is a good idea to talk about the difference between two terminologies, and the difference between two terminologies are a gas and a vapor. And those two words, a gas is something that in the normal sort of circumstance is found in the gas state. And a vapor is something that is normally not found in a gas state, but can be converted to a gas. And water is an example of that. Water, as we just talked about, normally found in the liquid state. You add a little heat to it. It's much and not too hard to get it to basically make steam, which is water in the gas state. So we don't usually call water like water gas, for example. We do call it water vapor to indicate, again, that it is normally found in the liquid state, but again, can be converted, obviously, into the gas state. As opposed to when we say like hydrogen gas, that again is normally how hydrogen is found, as in the gas state under normal conditions when it's not combined with anybody. How do we measure pressure? Well, one way that we measure pressure is through the use of what is known as a barometer. A barometer is an instrument that we use to measure pressure. Older barometers, which they've now taken out of most school labs and stuff like that, older barometers were really made out of a pool of mercury, hence why they've taken it out of the labs, and kind of a really badly drawn column of our tube that's in there. And as the atmospheric pressure sort of exerts on that pool of mercury, we start to see the mercury sort of rise in the tube. And mercury is a little unusual than most sort of liquids, if you will. It actually has a reverse or upside down meniscus. So remember, most meniscus go this way, where we read it at the bottom. Actually, for mercury, it goes the opposite way. We actually read it from the top of the curve when you're reading mercury. So if you ever were to see a mercury barometer and really looked at it, you would see more of a inverted sort of meniscus. And actually, in this case, we would read from the top of that. And that is really where the level would be. There are some units associated with pressure that we commonly see. One is an atmosphere, which is an ATM. No money, unfortunately. Other common units are a torr, named after the guy who invented the barometer, torr, and one mmHg. mmHg, this stands for millimeters of mercury. And the reason for that is when you go to an old traditional barometer, it is mercury. And when you look at the little tube that's sitting in there, they typically have a ruler. And that ruler, you would take a reading like you're reading a ruler. A lot of times is in inches, but then you oftentimes would convert it to millimeters. So that's where the millimeters part comes from, like reading it off a ruler. He is mercury, because typically the liquid that used to be in barometers is mercury. Nowadays, they kind of use alcohol sort of barometers and stuff like that. There is a relationship between these three sort of units, which we commonly see. By the way, there are other units that we come across. There's, PSI, which is pounds per square inch. Another unit of pressure is a bar, which is almost the same as an atmosphere. A Pascal or a kilopascal is another unit of pressure. But I would say for our class and most chemistry classes you take, these three guys here are pretty much the units that we see. And one torr is the same as a millimeter of mercury. And one atmosphere is the same as 760 millimeters of mercury and 760 torr. So clearly the 760 number is important. If you have atmospheres and you want to convert it into either millimeters of mercury or torr, you're going to multiply by the 760. That will give you millimeters of mercury or torr. Again, they are the same. So it's a one-to-one relationship between those two. Or if you're starting out with either millimeters of mercury or torr, you would divide by the 760. And again, we would end up with atmosphere. So that 760 number is a really important number to keep in mind. We do see it a lot, and we do this conversion a good amount of time. So again, we don't run into too much of the other sort of units here, and particularly this class, but those three for sure. Atmospheres, millimeters of mercury, and torr are definitely three units that we do see a lot. Any questions on that there? Here's a picture of a barometer, and as I mentioned, what it used to look like, again, we have this kind of pool mercury in there, hence the mercury rising is an old saying they used to do. And again, you do see these sort of you do see usually a ruler on these tubes. And again, that's where you would take your reading. You can see here, as I mentioned before, mercury a little unusual than most, has that meniscus sort of running the opposite way. And if we were to read it again, it would be sort of to the top there of the meniscus in this particular case. Again, as it sort of puts pressure on the bottom, mercury goes up the tube. So we're going to be looking at some different gas laws as we go through this sort of chapter here. And there's usually three sort of variables that we deal with. One is P, which is pressure. Another variable that we see a lot is V, which is volume. And T, which is temperature. So we'll see some formulas where maybe one is held constant, the other ones maybe could change. Maybe two is held constant, something else changes. But these are some common themes that we will see in these different gas laws. So let's talk about the first gas law, which is Boyle's law. And Boyle basically studied the relationship between pressure and volume. So in this case, he looked at pressure and volume, and he held temperature constant. And basically what Boyle saw was that a volume of a fixed amount of gas is inversely proportional to the gas pressure. So let's talk about sort of Boyle's law, which is in this box here. And this is sort of a lot of times like before something changes. This is sort of like after. Now, in terms of units, a couple of things in terms of this formula. The pressure can be any unit you want, as long as the P on the left-hand side and the P on the right-hand side there are the same units. And same thing with volume here. Volume could be any unit you want as long as they are the same. So V1 and V2 do have to be the same units for everything to cancel out. So basically what Boyle saw was when he held the temperature constant, as the pressure of the gas went up, the volume went down. So let's just think about, does that make sense? Well, if pressure is basically related to collisions, and if you take a sort of cylinder, if you will, where you have gas molecules flying around in this volume, and then decide you're going to drop the volume way down. You see by my picture here that pretty much I would expect by lowering that volume that they would increase the number of collisions that would occur. By increasing the number of collisions, I would expect the pressure to go up. And vice versa, the pressure goes down as the volume increases. And we can kind of see it looking from this way to this way. And this first picture on the right, obviously, as we just talked about, we would expect a lot of collisions to occur because the volume is very small. As we make the volume larger in the second picture going in that direction, now everybody has a little bit more room to fly around with. and it's going to take longer for collisions to occur. Longer for collisions to occur, we will start to see the pressure start to drop. So as one goes up in Boyle's law, the other goes down. Pressure goes up, volume goes down, volume goes down, pressure goes up in that particular case. Now, most cases you will be given probably information about 3 of the 4 things here. You need to basically solve for usually the 4th thing that's missing. And that's what this graph sort of shows us in terms of Boyle's law. We do see here pressure versus volume being graphed, and a much smaller volume down here. We see a much higher pressure than when we kind of make the volume much bigger, again, giving those gas molecules a lot more room to fly around, a lot longer until somebody collides. We do see a significant drop in the pressure over here, as opposed, again, if they're in that really small area, they got nowhere to go. It's just going to keep colliding, going to cause that pressure to go up, as opposed to a much bigger or larger volume, a lot more room to fly around with, a lot longer until they kind of make that collision. Any questions on that?
Professor, what is used to raise or increase the pressure or volume?
So for example, you could have an actual container that actually has, and I apologize for the bad drawing, but it has sort of a movable piston, if you will. And basically, you could start with a volume here, apply some pressure, which obviously would move this kind of piston down, and then it would kind of close down on the volume. And now your gas molecules would be compressed into the smaller volume. So you could actually use a container and kind of just almost like, kind of drop something down on it, and it'll trap all those gas molecules at a much smaller volume, and vice versa. If you sort of released it, right, and kind of brought it back up, it would increase the volume inside the container.
All right, thank you.
You're welcome. Other questions? Okay, so let's take a look at one here. So I want you to take a second or two here and see what you come up with. An inflated balloon has a volume of 0.55 liters. At 1 atmosphere goes to 6.5 kilometers. What is the pressure? Pressure is 0.4. What is the final volume of the balloon? So take a couple minutes to see what you come up with. At this point, we're going to talk about several others, obviously, before the chapter is over here. But oftentimes, if you just pull out the information from the problem and sort of label it, it will give you a pretty good idea as to, what gas law is probably the one you should use. So if I were to go through this problem, I would see, obviously, I have a volume here that is 0.55 liters. It's at sea level, which is 1 atmosphere. 1 atmosphere is a unit of pressure. So I would add that to my list there. It rises to 6.5 kilometers. That is actually, in this problem, useless information. We actually don't need it for anything. It goes to another pressure at some point here of 0.4 atmospheres. And lastly, we are assuming the temperature is constant, and we want to know what is the final volume. So again, if you had to maybe choose between different gas laws, this should kind of point out to you Boyle's law. You see 2 pressures, you see 2 volumes. So that should point out to you that perhaps Boyle's law is really the one that I should use here. Doesn't matter which ones you label as 1s and 2s. It really doesn't. Typically, people will just take the first things listed as the 1s, the second things listed as the 2s. The most important thing is you do obviously want to keep together the information that goes together. It's obviously 0.55 liters in 1 atmosphere. That pressure volume combination goes together, just like the 0.4 goes with what we're looking for. Now that we sort of have the right gas law, we can see that basically we do need to solve for V2. Now, in gas law sort of problems, there's a number of formulas. And just to, again, give you maybe a quick way to rearrange things sort of correctly is when we look at this, although it's not really written as a fraction, this really is sort of like a fraction with those guys, the P1 V1 on top, the P2 V2 on top. Whenever you move something across an equal sign, they will always end up in the opposite location of where they started. So in this particular case, we want to actually move the P2 to the other side. And basically it was on top on the right, which means when we move it over to the left-hand side, it will actually end up on the bottom. And that will give me the correctly rearranged equation of P1 V1 over P2 is equal to V2. And again, basically what we're doing is dividing both sides by P2. That's essentially what we're doing. But again, this sort of, in these formulas that we will see, you could think about each side as like a fraction. And again, basically this is how they move to the other side. Again, if it was on the bottom to start with and went to the other side, it would end up on top. Again, top goes to the bottom. So now that we have everybody sort of rearranged correctly, we just simply need to put our numbers in. So P1 here is 1 atmosphere. V1 is 0.55 liters divided by P2, which is 0.4 atmospheres. We're going to divide out the atmospheres, which is good. That leaves us 1 unit left, which is liters, which is also good because we are looking for a volume here. And we do end up with 1 times 0.55. I punch it in right, and there we go. And that's going to be divided by 0.4. That's going to yield me a 1.375 units here will be liters. Sig fig wise, everybody's got 2, which means we really should probably take this to 1.4. And again, the units here would be liters, which would match obviously what we're looking for there. First off, any questions on the calculation? Okay, so the other thing that's really important is to, again, understand sort of the relationships that happens with these different gas laws. So since we know this is Boyle's law, we know that the relationship is as the pressure goes up, the volume goes down, and vice versa. As the pressure goes down, the volume goes up. So let's think about what happened here. We started with a pressure of 1 atmosphere. We ended with a pressure of 0.4 atmospheres. So our pressure went down, which means that our volume should have went up. And we could double check to make sure we didn't screw up with the calculation. We see that our original volume here was 0.55, final volume 1.4. So it did match what we would expect to happen. Pressure went down, we see the volume goes up. So it's good to sort of understand those relationships because, you know, sometimes people invert numbers when they do these type of calculations. So again, if you get a number at the end that really doesn't make sense based on sort of what you would expect to happen with, say, Boyle's law or something like that, you know, you could double check your math. Any questions on that there, which is Boyle's law? The next sort of relationship we're going to look at is what is referred to as Charles' law. And actually, a guy by the name of Guy Lussick's law. Now, Charles' law basically looked at the relationship between volume and temperature, holding pressure constant. Guy Lussick's law, as we'll talk about here, dealt with really pressure and temperature, and he kept volume constant. So let's talk about really, you know, what we would expect to happen in sort of each of these situations. Let's start with sort of over here. So let's say we had a container where the volume is constant, basically. I'll draw 2 containers with equal constant volume here. Now we have gas molecules in there. If I increase the temperature of the gas molecules that are in this first container here, would we expect the gas molecules to start to fly around slower or faster? And hopefully the answer you would come up with is if you increase the temperature, the gas molecules will gain a lot more energy. As they gain a lot more energy, they will fly around faster. So in this situation here, we're going to get these gas molecules getting more energy from the higher temperature. They're going to fly around faster. There's going to be a lot more collisions. And because there's going to be a lot more collisions, because the volume is not going to move, we would expect the pressure to also increase that. Kind of like lighting a fire under somebody, right? They move faster. So same idea, gas molecules move faster as they're flying around faster with a lot more energy, more collisions leading to a much higher pressure. If we take the same sort of fixed volume and we lower the temperature, what's going to happen in this case is if we lower the temperature, that essentially is like removing energy from our gas molecules. And as the energy is removed, our gas molecules are going to fly around a lot slower. And if they're flying around a lot slower, I'll sort of demonstrate it here. And they're going to be moving around a lot slower. It's going to result in a lot less collisions occurring because they're moving slower. Less collisions occurring means that we would see the pressure start to go down. So if we keep that volume fixed and does not move, the temperature has a pretty good effect on the pressure that we see. Higher the temperature, more pressure, lower the temperature, lower the pressure. And that really is Guy-Lussac's law. And its law is P1 over T1 is equal to P2 over T2. And again, this is at constant volume. So what happens really sort of in Charles' law situation? Well, if we start with our same sort of container, but actually I want to draw it here, I think. But instead, this container is no longer fixed in terms of the volume. As we were talking about earlier, that kind of piston can kind of move up and down and kind of make the volume larger, make the volume smaller. When we increase the temperature in this situation, remember here, we want to keep the pressure constant. And if we increase the temperature and the volume does not move, we definitely will see a rise in pressure like we just talked about. But in order to keep it at constant pressure, what ends up happening is because those gas molecules are now moving around a lot faster, we're going to get a much greater increase in the rate of collision. So that would bring our pressure up. But to keep the pressure constant, what ends up happening is the volume of the container needs to adjust. And the volume of the container goes up. So what ends up happening is even though they're flying around faster, we adjust the volume to give them a lot more room to fly around in. And what that ultimately will do is keep the number of collisions relatively constant with each other. And as it keeps it relatively constant with each other, the collisions, we will see the pressure remaining relatively constant. So in Charles' law situation, the volume basically adjusts in a way to allow the number of collisions to remain constant and thus remaining the pressure constant. Opposite would be true if we did the lowering of the temperature in this situation. If we lower the temperature, and again, as I drew over here, the volume did not adjust, what would happen is we would start to see the pressure come down. But in Charles' law, we want to keep constant pressure. So what happens with the volume is it decides to decrease as well. So what this allows to happen is as those gas molecules are now moving around a lot slower, we're going to drop the volume in on them, and that's going to keep the number of collisions relatively constant. They don't have to travel as far to basically collide with the container. We're bringing the container to them. And again, it keeps those collisions constant. And by default, we'll keep the pressure constant as well. And that is really Charles' law relationship, which is down here, which is V1 over T1 is equal to V2 over T2. Now, there is a couple important things in here in these gas laws when we use them. And the first one is, it is the temperature. The temperature, and these gas laws and pretty much every gas law you come about pretty much does need to be in Kelvin. And it's a safe bet that if you are doing a gas law or using a gas law, you should definitely be using Kelvin as your temperature. Even if they ask you for the temperature in Celsius and they give you the temperature in Celsius, you need to convert it to Kelvin first, put it into the gas law, and then convert it out of Kelvin into Celsius. So definitely needs to be Kelvin for the temperatures. The volumes here for Charles' law doesn't matter, again, as long as they're the same on both sides. And the pressure here for Guy-Lussac's law does not matter as long as they are the same on both sides. So why do we need the temperature to be in Kelvin? Where our good friend Kelvin there basically realized the behavior of this. If we graph volume versus temperature in Celsius for any gas you choose, and you extend the line all the way back for every gas to the temperature, it always hits the exact same spot. And that exact same spot is what is minus 273.15 degrees Celsius. Kelvin called this basically absolute zero. And that is because if I wanted to convert this into Kelvin, I would then add the official number of 273.15, and that will give me 0 Kelvin, which is really absolute zero here. And a reminder again to convert the temperature into Kelvin. It is the temperature in Celsius plus 273. You don't really have to use the 0.15 unless you like to, but you can convert it into Kelvin by adding 273 to it. We do see what we talked about in terms of Charles' law relationship: lower temperature, smaller volume to keep the pressure constant, higher temperature, larger volume, again, to keep the number of collisions relatively constant. Any questions on that one there? All right, so obviously those gas laws you do need to know. So why don't you try one here, see what you come up with. We got an experiment that 452 milliliters of a gas in a light bulb heated from 22 to 187 at constant pressure. What is the final volume? So take a couple moments, see what you come up with. Pull out the information, sort of label what it is. You know, is it a volume? Is it a pressure? Is it a temperature? And again, that really will kind of point you in the right direction in terms of what gas law to use. At this point, we have a few to choose from. We have Boyle's law, as we saw earlier, which is P1, V1, P2, V2. We have Charles' law, which is V1, T1 is equal to V2, T2. And we have Guy-Lussac's law, which is P1, T1 equals P2, T2. So if we go through the problem here, we see 452 milliliters. That is definitely a volume. It's used for a light bulb that's heated from 22 degrees Celsius, which is a temperature, to a temperature of 187 degrees Celsius, and we're looking for the final volume. So again, you can see I have no pressures given to me. It's actually a constant pressure, which means Boyle's law is not really the right one. But we definitely don't have pressure either for this guy. Again, you could actually almost see Charles' law here when you just label these guys. And again, that will hopefully point you in the right direction of what gas law is sort of the appropriate one to use. So in this case, we have V1 over T1 is equal to V2 over T2. Remember that the volume here, there is no real restriction, but definitely the temperature. So before you get too far into it, you do want to convert into Kelvin just to make sure you don't forget to do that. So we do want to add 273 to each of these temperatures. That's going to yield me a 295 Kelvin. And again, we'll add a 273 here, and that's going to get me a 460 Kelvin. So again, if it's a gas law and you need a temperature, it definitely should be in Kelvin. Otherwise, you most likely will get it incorrect. In this case, we could actually just check off what we got going on. We obviously have V1 and T1, and we do have T2. So the goal here is basically to get V2 by itself. So a reminder that, again, you could basically multiply the both sides, which is the same thing as what I'm going to tell you to do now. Or you could just simply go, I need to move this guy to the other side. It's on the bottom here, which means when it goes across the equal sign, it will end up on top. That will give you the correct way to rearrange this equation. And that would equal V2, which is ultimately what we're looking to solve for. At this point, we want to make sure that we do put the correct numbers in the correct location. So V1 is 452. T2 is actually what we need on top, which is the 460. And T1 is on the bottom, which is actually the 295 Kelvin. Here, the Kelvin up on top and the Kelvin on the bottom will cancel each other out. And we end up with 452 times 460, if I can get that in my calculator, divided by 295. Looks like we end up with something like 705. And the units that are left in this particular case are milliliters. So I think I said 705 milliliters. First off, any questions on the calculation? Again, we could kind of think about, does our answer make sense based on what we know about Charles' law? What we know about Charles' law is what we talked about on the previous slide. We know that because it's constant pressure, we would expect that as the temperature increases, the volume should increase to keep the pressure constant. And as the temperature decreases, the volume will get smaller again to keep us at constant pressure. So let's see if that's actually what we saw here. In this particular case, we started at 295 Kelvin. We ended at 460 Kelvin. That means that our temperature went up, which means we should see the volume also go up. So we started at 452. We ended at 705. So again, that does really match what we would expect to happen in terms of the trend that we see for our good friend there, Charles' law. Any questions on that calculation or how we got the numbers? Or
Professor, if we needed to, if they were asking for the temperature and it originally started Celsius, then we convert to Kelvin, then as a final answer, will we have to convert back to Celsius?
It would depend on the question. If the question did ask for it in Celsius, you would need to convert back to Celsius by subtracting 273 at that point. If it just sort of generically said, you know, what is the temperature, you could probably just leave it in Kelvin, but it would be sort of problem specific on that. But again, as I mentioned before, there are some problems, and sometimes people, especially using like Charles' law or any of these other ones that have the temperature component, sometimes, for example, they're given like, hey, the temperature is 185 degrees Celsius. What's like the final temperature in Celsius? So sometimes when people see this, they go, oh, they gave it to me in Celsius and I need to give the answer in Celsius. So it wouldn't make sense. Hey, let me just throw it into the gas law in Celsius, and you will get the wrong answer. So you do have to, even if they give it to you in Celsius, they want the answer in Celsius. In between, you got to go to Kelvin, then into the gas law, and then convert back to Celsius on the back end. So again, sometimes people miss that step, and it is sort of logical in that sense. People just think, well, again, you know, they gave it to me in Celsius, we want it in Celsius, why can't I just throw it into the gas law in Celsius? And again, you will not get the right answer. So definitely got to be Kelvin in there. And to answer your question, like I said earlier, it is sort of question dependent as to what they're asking for. So if they're really specific, like give the answer in this unit, you want to make sure that you do that.
Okay, thank you.
You're welcome. Other questions?
And that would also apply for Fahrenheit, right?
It would, and to be truthfully honest with you, you probably won't see too much Fahrenheit, but yeah, if for some weird problem, you were given the temperature in Fahrenheit, you would actually need to take it from Fahrenheit to Celsius and then Celsius to Kelvin, put it into the gas law. And then again, if they wanted it in Fahrenheit, you would have to go backwards on that conversion at the end. After you solve the gas law, go from Kelvin to Celsius to Fahrenheit. Other questions? Okay. So let us finish up talking about here sort of the granddaddy of them all here. If we put together Boyle's law, which is what we saw earlier, P1 V1 equals P2 V2. Charles' law, which is V1 T1 is equal to V2 T2. Dialusic's law, which is P1 T1 equals P2 T2. And our good friend Avogadro, which he has a number, he also has a law, and Avogadro's law is actually V1 over N1 is equal to V2 over N2. Avogadro's law is kind of an interesting one. It is actually at constant temperature and pressure. And N is the number of moles of a gas. And in this particular case, putting all these together gives us the ideal gas law, which is right here, which is PV equals nRT. A couple of things about an ideal gas. An ideal gas, as we'll talk about towards the end of this chapter, is basically pretty much all the gases we deal with in this class. There are certain gases which are referred to as real gases, but for everything in this class, you could pretty much assume that it's an ideal gas. And again, later on, we'll talk about really what that means. But the other really major thing here about PV equals nRT, if you compare it to any of these other sort of gas laws before it is really a sort of one and done situation, which means there is no two pressures, there's no two volumes, there's no two temperatures. You have one pressure, one volume, one temperature, and so forth. It is also, out of all of them, the most restrictive in terms of units. When you use the ideal gas law, the pressure, which is P, has to be in units of atmospheres 100% of the time if you're going to use the ideal gas law. The unit of volume needs to be liters if you're using the ideal gas law. N is moles, and it does need to be in units of moles. And again, if you're not sure what moles is, again, I suggest you do watch the chapter 7 video. We talk about moles there, so that will make more sense. And T, which is temperature, and as we talked about before, it also does need to be in Kelvin. You may be wondering, why does all of these guys have to be specifically in those units? And it's really because of the guy right there, which is R, this guy. R, which is the gas constant, which means it's a constant value, and it has a value of 0.08206. Some people do round it. I personally don't, because that's the number they beat in my head. But sometimes people will round it to 0.0821. And more importantly, the units that are associated with the gas constant are liters times atmosphere divided by Kelvin times mole. So that is why every one of these other units here has to be in those units for everything to properly cancel out with R. The other good news is, if you for some reason can't remember what units everybody should be in, and you have the value of R given to you, which you most likely will, you could just simply look at the units there, and then you will know every unit that everybody else needs to basically be in. We use this, as you can see, to solve for anything that's there. We could solve for moles, we could solve for P, we could solve for V, we could solve for T. And again, you always have that R value given to you, or not given to you, but you always have it. It is not always given to you in the actual problem that you're doing, So you should always keep in the back of your mind, if like you have everything but like R, that is a value that you always sort of have. So, you should always have that available to you. So I think based on time here, we will lay it up. A reminder, as I mentioned a little bit earlier,